Good day to you, students. Last class we discussed about seismic waves. For the past two class, we are discussing on seismic waves, how it propagates, what are the types, and what are the classification. So we discussed all the basic things about seismic waves. Today in our class, we are going to discuss on seismic waves. What is the another part of seismic waves, and what is the impact on it in worldwide. So in worldwide, what are all the impacts and especially today is a special session to look into the origin of tsunami. So how tsunami originates from the seismic waves. So we are going to discuss on the topic also. So now I am going to present my screen. So seismic waves and tsunami, we are going to discuss it. What are seismic waves? Last class we discussed about that, and uh, you have the solutions for all the questions from the previous classes. Where are they? What do waves do? How many different types of waves are there? Or waves are important to all of us, and why or why not? Name different types of waves. So types of waves. These are the basic classification and their types. So first thing, uh, body waves. The broad classification is the body waves and surface waves. Remember the seismic waves which are traveling inside the body of Earth, we call it as a body waves. The seismic waves which are travel on the surface of the Earth, we call it as a surface waves. So body waves which are primary and secondary waves, the P wave and S wave. P wave origin reaches the station first, and the secondary wave which reaches the station next to the primary wave. Then surface wave, Love wave, and Rayleigh wave. Love and Rayleigh are the scientists who discovered the types of waves. And seismic waves are the waves of energy caused by the sudden breaking of rock within the earth or explosion. They are the energy that travels through the earth and is recorded on seismographs. There are several different kinds of seismic waves, and they all move in different waves. The two main types of seismic waves are body waves and surface waves. Okay, so these are all the important things about seismic waves. So let us discuss some things in detail. If you missed out the last class, I will recap some of the stories from the last class. So the first kind of a body wave is a P wave, primary wave. This is the fastest kind of seismic wave. It can travel through solid rocks and fluids like water or the liquid layers of air. It pushes and pulls the rock. It moves through just like sound waves push and pull the air. P waves. So this is what we call the compressional wave, compressional and dilation of. Have you heard a big clap of thunder and heard the windows rattle at the same time? So the windows rattled because the sound waves were pushing and pulling on the windows glass, much like P waves push and pull on rocks. Sometimes animals can hear the P waves of an earthquake. Usually, we only feel the bump and the rattle of these waves. The next wave, body waves, type of body wave is S wave, that is the transverse wave. The transverse wave, S wave, which is the second wave you feel, that is it reaches the station next to the P wave. And S wave is slower than P wave and it can move only through the solid rocks. This is the important characteristic of this S wave. So this wave moves rock up and down or side to side. That's why we are having the P wave shadow zone and the S wave shadow zones are there. Last class we discussed. If you missed the last class, you can go through the video of the previous class and you can get into the knowledge of this velocity and the seismic shadow zones. Then surface waves, which is the first kind of surface wave. A.H. Love, a British mathematician who worked out this mathematical model for this kind of wave in 1911. It is the fastest surface wave and moves through the ground from side to side. Rayleigh waves, the other kind of surface wave is the Rayleigh wave, named after the scientist John William Struck. Lord Rayleigh, who mathematically predicted the existence of this kind of wave in 1885. A Rayleigh wave rolls along the ground just like wave rolls across a lake or an ocean. Because it rolls, it moves the ground up and down and side by side in the same direction that the wave is moving. Most of the shaking felt from the earthquake is due to the Rayleigh wave, which can be much larger than the other waves. So, how seismology helps? So, seismology helps to determine what is inside the earth. That is, the internal structure of the earth can be calculated using this seismic waves. If an earthquake originated at a particular place, the wave should reaches the station expected uh, position is the first wave. You can see this wave which is the expected position. But unfortunately, if we have the components, that is the geological components, the variations due to the geological variation, the log surface, different composition of air, the velocity will vary and the arrival time will be somewhat differing. That is, the expected will be here, but we can get this here. The waves we can get this here. This is because it's the content which lower the velocity body in the mantle. Okay, so that's why we can use different stations to measure the seismic signals so that what is inside the earth can be obtained. So the low velocity body lies in here. More ray paths will tighten the fix. So such kind of information, useful information, can be obtained only through this seismic waves. So in Hawaiian Island, you can see how much fast and how much slower the seismic waves are traveling. So up to the depth of that certain kilometer, the red heart which shows the slow speed of the seismic waves, the blue cold region says the fast um, the velocity which is faster uh, at these regions. So different ways of measuring the earthquakes, that is the Mercalli intensity scale. First one, recorded only by seismographs. So we are classified the intensity of earthquakes based on the magnitude. So if the magnitude is 9.1 and 6, 7, so all the things they are classified based on the damage it makes. So first recorded only if the scale, the modified intensity scale is 1, then it will be recorded only by the seismographs. In if it is 2 and 3, it will be felt by some people who are indoors. So 4 felt by many people, windows will rattle. So then 5, flight building damage, plaster cracks, bricks will fall. 6 and 7, much building damage, chimneys fall, houses move on foundations. So 8 and 9, serious damage, bridges twisted, wall fractured, many masonry buildings collapse. 9, 10, and 11 and 12, which bring the greatest damage, that is, most buildings will collapse. Total damage, where you see on ground surface, objects thrown into the air. That is, on 12, you can see tsunamis. So different types of measuring the earthquake depends on the earthquake size and that depends on the fault type. So here you can see the seismic tomography, that is the subduction zones. So how the subduction zones can be measured. What is subduction zone? Subduction zone is the region of the earth crust where the tectonic plates meet. So the tectonic plates are massive pieces of earth crust that interact within each other. The places where these plates meet are called plate boundaries. That is what we call the subduction zone. So many subduction zones are there, and the subduction zones may result in geohazards like earthquakes and mainly volcanoes. So the volcanoes are mainly found in these subduction zones. So the subduction zone is one of the important phenomena in seismology. So when two tectonic plates meet at a subduction zone, one bends and one slides underneath the other, curving down into the mantle. So this kind of reaction takes place, and it was first identified by scientists in 1960 when there is a descending crust across that they discovered the shifting tectonic plates. So this kind of movement of subduction zones have huge boundaries and can generate very large earthquakes. So the size of the earthquake is related to the size of the fault that causes it, and the subduction zone faults are the longest and widest in the world. So these are called the subduction zones. So the P-wave tomography, which says where the subduction zone is there and how it happens. The blue line show the intensity of this subduction zones. So when subduction zone earthquakes hit, and definitely the earthquake magnitude will be greater than 7.5. So that is more important. And as tectonic plate slides into the mantle, the hotter beneath layer of earth crust, the layer beneath the earth crust, that is the heating releases fluids trapped in the plate. These fluids such as seawater and carbon dioxide rise up to the upper plate and can partially melt in the overlying crust, forming the magma. So this magma will erupt from the volcanoes, and some of the main volcanoes are found on this plate boundaries. So we call it as the ring of fire in the Pacific region. So this where you can see large amount of subduction zones are there. So beneath the subduction zone, what is there, and everything has been given. Richter, based on the Richter number scale, how many magnitudes of Earth happen every year, and up to 1900 to 2000, how many earthquakes happen around the magnitude of 7.5 and 8 is shown the scale, approximately around 5 magnitude every year. More number of earthquakes are happening. So earthquakes are bad to us, and let us see one by one. So what is earthquake and how it happens, and let me list out some of the important and significant earthquake that happened in the history of Earth. And in Olympia, the earthquake hit in 1965. So this earthquake, it hit at Olympia 1965 at 8:28 a.m. So this earthquake, which causes the severe damage, and it produces a lot of damage to the buildings and constructions. So the total damage is estimated around 12.5 to 28 million dollars. The magnitude is around 6.7 magnitude. So you can see this the classification. So 6.7 to 7, that is a much damage, building damage, and the chimneys fall, houses move on foundations. So this earthquake is one of the Olympia earthquake is one of the significant earthquakes which is falling under the range of 6 and 7 Bessel intensity scale. So in 1965, April 29, it happened in the southern region of Washington, sorry, to the sound region of Washington, United States. So this earthquake, aftermath effect of these earthquakes, results in the Pacific Northwest Seismic Network in 1969. So this is one of the prominent earthquakes in the history. And the next one, which is the earthquakes of Seattle 2001. Seattle's 2001 earthquake is one of the important earthquakes happened in the history. So this earthquake happened in the Pacific Northwest, the Pacific Northwest region in 2001. So this magnitude is around a 6.8 magnitude, and it creates 1 to 4 billion dollar total damage to the society, so to the environment. So it affected the Pacific Northwest. So this is one of the important earthquake, and the next one, Shishi Taiwan earthquake in 1999. This is a Chinese earthquake. It happened in Shishi Taiwan earthquake, 1999. So it happened in September 21 with a magnitude of 7.3 to 7.7 magnitude, and it created damage for about the casualties around 2,415 casualties died, and it created a lot of damage to the buildings and materials and constructions and build and some were missing around the 32 29 to 30 members were missed. A lot of people injured. The depth of the earthquake is 33 kilometers beneath the surface. So this is one of the important earthquake in the history. And Elsewhere earthquake 2001. So see how much stretch it happened. So Elsewhere earthquake. So this earthquake is one of the important earthquake in the history. It happened and it created the magnitude of 7.6 in the 7.6 magnitude. It recorded the magnitude and total fatalities 944 fatalities at this earthquake and a depth around 60 kilometers beneath the surface. This happened in January 13, 2001. So, Bang Iran, these are all some earthquakes, examples of some earthquakes in 2003. And earthquakes are dangerous, and that's Sichuan, China in 2008 earthquakes, Japan 2011 earthquakes. Let us see this Japan 2011 earthquakes, which is one of the prominent earthquake, and this happened every year. Japan is severely affected. This is because of its lying in the seismic tectonic plate boundary zone. We call it as a ring of fire zone. Let us see in one more in the upcoming slide. We can see there's how much impact is creating every year in the ring of fire zone that is in the Pacific coast. So this earthquake happened beneath the 29 kilometer and around total damage of around $360 billion. So it's one of the violent earthquake. The maximum intensity scale is 9. So measured the Messal intensity scale, which is 9. And the tsunami it created tsunami around 40.5-meter height tsunami at Tohaku and around 15,899 people died in this tsunami and earthquake. The peak ground acceleration and the peak velocity are very high during this earthquake. So it happened in 11th March of 2011 with a magnitude of 9 to 9.1. It brought severe damage to the building and a lot of people died. See, this is the pattern of a global earthquakes so far up to date. So, how many earthquakes happened? So, here it is the ring of fire zone. So, starting from Japan, Indonesia, Sumatra up to Andaman. So, this is the ring of fire zone. So, this is in India. We are having the Himalayan plate, the Himalayan boundary. There you can see the large number of earthquakes happen. Why? Why the Everest is so high? That is because of this the boundaries. So three types of boundaries are there: divergent boundary, convergent boundary, and transform boundary. So when one layer linked with another layer, that is, if it touches, either it will go up or it will go down. So when two continental plates converge, they smash together and create mountains. So there is a convergent boundary in the Himalayas. So the Himalayan mountain, that is the plate between Indian plate and Eurasian plate, there is a convergent plate boundary there at the Himalayas. So when two plates merge together, they smash together and they created the mountains. So these mountains, which produce the continental shift, so between the Indian plate and the Eurasian plate. So that's why Everest is so high, around 8,000 meters approximately. So 8 kilometers from the sea level. So it's the highest in the world. So that is because of this convergent plate boundary. So this is due to the tectonic plates. Okay, so uh, the ocean continent convergence results in two continents collide and produce this mountains. Next, world seismicity, you can see 1971 to 1992, how it happens and how many earthquakes are there, around 0 to 70 earthquakes black regions. So yes, a shake maps you can see, and different types of earthquakes and some of the examples I have given here. So Loma Prieta earthquake in 1980. And one more thing I want to discuss in this previous slide, which is uh, fault zones. So here you can see South American plate, you can see the San Andreas fault. So this San Andreas fault zone is one of the important fault zone in California. So in the world, it is located in a North American plate, and which contains the continental transform fault. So San Andreas Fault is located in California, and it is the junction of tectonic boundary between the Pacific Plate and the North American Plate. So this one is a fault. Actually, the fault is the zone. The seismic fault means the zone where this seismic intensity created the impact. So seismic fault means it's a planar fracture. So a discontinuity in the complete volume of rock across, where you can see the significant displacement as a result of rock mass movements. Okay, so fault is a planar fracture. You can say it's a fracture. So the San Andreas fault is the San Andreas fault, where you can see more number of earthquakes are happening every year. So some of the things happened inside the ocean, so that created some tsunamis or some mountains inside the ocean. Some when the volcanic eruption happened, what will happen? It will be freezed, and it created lot of minerals, and that minerals were expelled out in the ocean, and that produced a lot of coral reefs and natural resources. So inside the ocean, there are many mountains. So these mountains are from the volcanic eruption of these earthquakes. Okay, so that is I want to say in between. So here you can see how the Mercalli scale intensity scale varies. That is 6, 7, 9, 8, and 5. All the scales they have mentioned here in the Loma Prieta earthquake of 1989. So Northridge earthquake of 1994, you can see the severe several damage here. The San Francisco and New Madrid earthquake, and extent of earthquake varies widely. So this is a map. So some of the equipment that uses the seismic measurement. So this is the logarithmic scale on the larger displacement that you can see Wood Anderson torsion seismometer. So Wood Anderson is the seismometer, and this Anderson seismometer. Once in our college, a student designed a seismometer to record the earthquakes. So that is based on the Wood Anderson seismometer, and he devised the instrument based on the mechanical springs and uh, using the ball, the large huge mass ball. Based on that, he discovered the he devised the instrument. So it was one of the important MSc project, and he got wonderful marks in that project. Based on this project, he was credited with a more number of marks. So the equivalency of magnitude and energy. So for example, if the energy released, so you can see how much TNT, that is trinitrotoluene, how much energy. Small atom bomb can produce 6 tons of trinitrotoluene, which produces the impact of 4 Richter scale magnitude. So the comparison between the trinitrotoluene, that is the TNT, with Richter magnitude, you can see that is 9 magnitude. It will be around 1 99999 tons of energy of TNT is released during this kind of earthquakes. So the moment magnitude and fault length and the duration of shaking that classified according to the University of Connecticut. So you can see this moment magnitude, fault length, and duration of shaking. So tsunami, we shall discuss this tsunami in next class. So today this class is very important, and you might have learned some things about seismic waves, and uh, we shall continue with the tsunami waves in the next class. So the seismic fault zones, the seismic rupture zones, and how it impact the environment and the society we have discussed today. So this is very important. This kind of seismic waves uh, are very important, are very useful to determine the internal structure of Earth. So with this, we shall wind up. And one more thing I want to discuss about the seismic waves or the classification. That is, love waves and the Rayleigh waves are more important surface waves which produce a lot of damage to the society. So remember, it's not the body waves; it is the love waves and Rayleigh waves which created a lot of impact on the environment. So that's why I am insisting you to study how the these seismic wave. Do you know it is we are studying just labeling thing, that is if we are reading just a label of the seismic waves, that is what is body wave, what is surface wave, like that, but it's not important. We need to know the mathematical model, how to model this love wave and Rayleigh wave, how the motions between side by side are moving, how to model it. That is more important than studying all the labeling features. So, first thing, mathematical model is more important if you want to elaborate a physical mechanism. So, if there is a dynamics, how to explain it in mathematics, that is more important. So, it is very difficult. You need to get into some of the basic differential calculus, and you have to elaborate those things with the dynamism, that is the iterations. So, when if the time varies, how the things are iterating and how it is damping, all the things you need to study. So that is more important. That's why I'm insisting you to study the mathematical model. So if possible, if you are interested, let me forward some of the books in our classroom. You can study those things, and the mathematical model will be available, and you can go through the mathematical model based on that. Okay. So today we are winding up the session, and if you have any comments or queries or any suggestions, you can post it in the YouTube channel, or else you can post it in the classroom also. Okay, so that's all for today. Thank you so much, all the students. Thank you.